Hello everyone. I'm Swati and I'm presenting the paper review on transfer learning. These are the people links and the Medium article link, and this PPT can be found on SlideShare, and all the links have been given in the GitHub. Let us understand what is transfer learning. So transfer learning is a method under research in machine learning that stores the knowledge obtained from solving one problem and uses it to solve problems that are different but related to the solved one. In other words, it basically initializes a model by having another model's weight as reference. Since training a model takes more computational power, time, data, transfer learning helps at reducing this by improving the learning accuracy. Basically, the target learner learns from the model which is already trained initially by using the stored knowledge. So we can see in this figure that task X uses a pre-trained model and it stores the knowledge, and the new model, and then the new model is used to solve task Y. So task X and task Y here are different but they are related. So let us talk about real life applications of transfer learning. So in real world, if a person knows how to ride a bicycle, he can learn to ride a motorcycle easily. Or if someone knows how to play a violin, can learn to play piano quicker than someone who doesn't know how to play a violin, because they both have the common characteristics that they both are musical instruments. So one thing we have to keep in mind that it is not necessary that transfer learning always have a positive outcome with the newer data that is available. If the shared characteristics between the domains are very small, the transfer of knowledge from the source domain to the target learner, it will not be of much use. So in simpler words, if someone who knows how to play a piano, that doesn't help the person to learn how to ride a bicycle faster, right? So this is called as negative transfer. Yeah, there are two main categories based on differences in domain: homogeneous transfer learning and heterogeneous transfer learning. In homogeneous transfer learning, it basically handles the situations where domains are of similar feature space and there is only a small marginal difference between the domains. So these differences, they can be rectified by correcting the covariate shift or sampling selection bias. So this correction is only possible in some cases. So let us take an example of sentiment classification, as one word may mean different according to a situation, right? So that is not, homogeneous transfer learning is not very useful in such cases. A heterogeneous transfer learning, it handles situations with domains of different feature spaces. There is a connection between transfer learning and machine learning tasks. First, we'll talk about semi-supervised learning. So, what is semi-supervised learning? Supervised learning consists of completely labeled instances. Unsupervised consists of no labeled instances, and semi-supervised, it basically reduces the labeling cost because it reduces the dependency on the labeled instances. It it basically draws both labeled and unlabeled instances from the same distribution. This is where it differs from transfer learning, because in in transfer learning the source and the target domains differ, and they do have so transfer learning does adopt a few concepts from semi supervised learning. Next, we'll talk about multi-view learning. It solves ML problem that has multi-view data. So what is a view? A view is a distinct feature set. An example of multi-view learning would be a video object with two viewpoints. So there is an image signal as well as an audio signal. That and it has a vast amount of information, right? So multi-view techniques adopt multiple strategies, namely multi-kernel training, subspace learning, and co-training, and these are also used in transfer learning. Now we'll talk about multitask learning. It transfers the knowledge in related domains, but transfer learning transfers the knowledge while simultaneously learning the related task. So multitask learning, it focuses on all tasks, but transfer learning focuses more on the target tasks, right, than the source task, because that is where we'll be using the stored knowledge. So they do have a few similarities. They both aim at improving the learner's performance by transferring knowledge, and they have similar strategies for model construction, such as parameters sharing and feature transformations. These are the categories of transfer learning. In transfer learning, there is a categorization of problems as well as solutions. In problem categorization, we have label setting based categorization that further is of three types. First one is transductive transfer learning. It deals with the problems where label information is obtained only from the source domain. Inductive transfer learning deals with the problems where label information of target domain instances is present, and unsupervised transfer learning deals with problems where label information is unknown in both target and source domains. So in space setting based categorization, the problems are of two types: homogeneous transfer learning and heterogeneous transfer learning, which we have already discussed earlier. And for the solution categorization, that is majorly of four types. The first is instance based approach. It deals with instance weighting strategy, and it basically reweights the samples in the source domain to correct the differences in the marginal distribution. So these reweighted instances, they are used in target domain training. Next comes the feature based approach. It transforms the actual features in order to create new feature representations. So these approaches, they are of two subcategories. One is symmetric transformation, the other one is asymmetric transformation. So asymmetric approach, it basically transforms the feature in the source domain to match the ones that are in the target domain. And symmetric approach, they find a common latent feature and transform the source and target features into a whole new feature representation, unlike asymmetric one. And the parameter based approach, they transfer the knowledge at model or parameter level, and for relational based approach, they focus on problems in the relational domains. So transfer learning approaches, they have interpretations from both data and model perspectives. So this is from a data perspective. So if we see here, the first one is instance weighting strategy. So for this, let's consider a scenario with many labeled source domain instances and limited target domain instances, right? And let's suppose that both differ with a marginal distribution. So we can take an example of building a model to diagnose diabetes, right, in a particular region where older people are in the majority. So target domain instances are limited, and the data is available from different region where younger people are in majority, suppose. So our source domain has more of older people and the target domain has more of younger people. So transferring data directly from one region to another is not possible due to the marginal distribution difference, and older people have a higher chance of having diabetes as compared to younger people. This is where weights come into picture, and weights are assigned to the source domain instances in the loss function to reduce this marginal distribution difference. Now let's talk about the feature transformation strategy. Let's consider an example of cross-domain text classification. This particular task, it involves constructing a target classifier using labeled text data from a related domain. So the best solution for this particular scenario would be to find the common latent features using feature transformation and using them as the bridge to knowledge transfer. So the construction of these new features minimizes the marginal and conditional distribution difference while preserving the properties or structure of data and finding relations between these features. So the feature transformation is further divided into three subcategories: feature augmentation, feature reduction, and feature ailment. Coming to feature augmentation basically have subcategories as feature replication and features stacking, and they transform features by feature replication. Okay. In case of single source transfer learning, the feature space is augmented up at least 3 times. So if we have a feature space of 1, it will be augmented up to 3 times. So you will have the data set that is multiplied into 3 times. And the new features consist of the general features that are present, and also the target and source specific features. Next comes the feature mapping, that is part of feature reduction. So we are aware of principal component analysis. So that is one of the most feasible mapping based methods for extracting features, and PCA focuses on data variance rather than these data distribution differences. Next is the feature clustering. It aims at finding abstract representation of features of the original features. So few transfer learning approaches, they aim at reducing the features by co-clustering techniques, which cluster the rows and columns of contingency tables simultaneously based on information theory. So if you want to learn more about co-clustering techniques, you can find more information on my Medium article. Next comes the feature encoding. It is as important as feature selection and extraction. So it basically uses autoencoders. So what are autoencoders? Autoencoders, they have an encoder and a decoder. The encoder produces an abstract representation of the input, and the decoder aims at minimizing the reconstruction error. So autoencoders can be stacked one top of the other, and so after the training process of one particular autoencoder, another autoencoder basically can be stacked on top of it. So the new autoencoder which is added is trained using encoded output of the autoencoder of the upper level as its input. Next comes the feature alignment. So feature alignment primarily focuses on explicit and implicit features such as statistical or subspace and spectral features, as it has been mentioned here. And it is a very important step in feature transformation. So many types of features can be aligned, including spectral and subspace features. This figure shows the corresponding strategies and objectives of transfer learning from a model perspective. So the first one is model control strategy. So during the training process, the knowledge is pre-obtained in a pre-obtained source model is transferable to the target model, as we have seen in the previous slides. So in many frameworks are developed for multi-source transfer learning. So one example is domain adaptation machine. The main goal of domain adaptation machine is to construct a robust classifier for the target domain with the help of few base classifiers pre-obtained and trained on various source domains. Right. Next is the parameter control strategy. It majorly focuses on model parameters. In the case of object categorization, the knowledge obtained from the source categories can be transferred to target categories with the help of object attributes such as color or shape. The probabilistic distribution parameters of these image feature correspond to each attribute learned from the source domain, which helps the target domain classifier. So these parameters, they basically reflect the knowledge that which particular model learns. Next is model ensemble. Suppose for sentiment analysis application for product reviews from multiple product domain data or models are available. So the distribution of the domains, they differ, and combining the data and or the models is not the most efficient way to do it. During those times, model ensembling is a commonly used strategy. Next is the deep learning technique. So there are many researchers who use deep learning techniques in construction of transfer learning models. The two types of deep learning approaches are traditional deep learning and adversarial deep learning. Let us talk about the applications of transfer learning. It has been extensively used over years, and they are majorly aimed at solving text and image related problems. So, apart from the traditional text and image related problem solving, they have also found their application in medical, bioinformatics, transportation, and recommender system. So let us talk about medical application. So one of the areas in which transfer learning is used is in detection of Alzheimer's disease. So the MRI images from the target domain, they undergo pre-processing, and there's an architecture called as AlexNet that is trained using ImageNet as source domain for learning new tasks. So the transfer learning convolutional layers are fixed with one fully connected layer and an output layer. So the modified AlexNet architecture is trained on these Alzheimer dataset, which is the target domain, and they have proved to provide higher accuracies for multi-class classification problems. Next is the bioinformatics application. So gene expression analysis, it predicts the association between genes and phenotypes. A challenge faced by this is that the data that is available for training or testing, that is limited. So transfer learning helps in overcoming these issues by leveraging additional information and knowledge. The third application is transportation application. For understanding the traffic scene images, transfer learning is very helpful. There might be disturbances in a particular image due to the location issues, such as the weather might not be favorable or the light conditions might not be good. So transfer learning can help in vehicle type detection, traffic signal recognition, and if there are any irregular activities going on, it can detect that as well. The fourth one is recommender system application. So historical data is not abundant, right? So such issues can be solved using transfer learning. It can use the data from various recommender system that will serve as our source domain to construct a recommendation in the target domain. Thank you.